Everybody, how you doing? I got to applaud you. You stuck around to the end. Good job. And people left already. Your fault. My name is Pete Bagley. I'm one of the guys helping out the speakers coming through, and Brian's going to share some information with you on Fuzzing. Brian right now is tied to Guard Point Security, where he's one of the smarter guys over there. That's why we asked for him. But no, he's actually doing really good stuff from the Windows side, also from the Linux side. So we're going to catch both OSs depending on where you work in. Okay. Without further ado, all right.
Obviously, you're here to see talk about fuzzing. I've been kind of really digging into that this year and doing some research. It kind of occurred to me that there's a lot of real good use for just kind of the basics introduction, especially for developers who may not integrate that into their SDLC, as well as hackers who are looking to find some more bugs. Whether you're doing your own research or you're actually a consultant or something like that. So this is an intro to fuzzing for hackers and developers. So to start off, just fuzzing itself is basically just kind of throwing random data or kind of unexpected input at an application to see how it behaves. You're really looking to see, like, in these circumstances, if you get this kind of wacky off-the-wall file or input, what does the program do? If you're a hacker, you're looking for hopefully some kind of memory corruption that you could use for exploitation purposes. If you're a developer, then obviously you're going to want that as well, but also some more generic things like assertion errors or memory leaks and stuff like that. Fuzzing is useful for each of those situations. So that's fuzzing. This is intended for both hackers and developers. So what do I mean by hackers? Well, just kind of people who are looking for bugs in software. What do I mean by developers? People who are looking for software. It's the same mindset. It's the same, tools that you're going to use, the same, outcome. But you're probably going to be looking at it from a different perspective depending on where you're coming from. Again, there's a little bit more things that you're going to be interested in as a developer, but it's a super useful tool for hackers as well. So hackers and developers are both looking at this technique that they can use to find bugs, and ultimately they're just trying to answer the question, what happens when this application is given unexpected input? So fuzzing helps a lot with figuring out how robust your application is. If you've got an application that is just making assumptions, and those assumptions hold true when you're given valid input, but the second that you get something that's a little bit off the wall, then everything goes haywire and crashes, which is a good thing for hackers, not so much for developers, when you have a good time. So fuzzing isn't necessarily going to help you find maybe race conditions or logic errors. It can sometimes, but for the most part, you really see a lot of success in finding memory corruption, which is great for hackers. So, 3 things I want to really highlight today. Fuzzing is really effective. It doesn't take that much effort to get started in fuzzing. You're going to find bugs just from not that much of an investment. I say that not necessarily in high-value targets, but if you've got your own application, if you're consulting, there's going to be bugs there, and fuzzing is a great way to find them. So secondly, anyone can, and in my opinion, should be doing software fuzzing. It's not that difficult. It's your friend. It's not something to be afraid of. And it's so effective that it's something everybody should be doing. And it's approachable, too. That being said, fuzzing is easy, it's approachable, it's your friend, but there's a lot of really advanced techniques that can be used as well. Easy to learn, hard to master. So we'll talk about kind of, in an introductory phase, some of the really simple ways to get started, and then at the end we got kind of a little bit more advanced stuff we can do. So, taking a look at key takeaway number 1, fuzzing is effective. I actually had to add a little caveat here. Fuzzing is effective, especially when you're running against native code versus managed code. So managed code like .NET or Java or something like that. It's managed code. So the runtime, either the .NET CLR or Java runtime environment, it manages the code. So it's going to make sure that there aren't really stupid flows and stuff like that. Now, could you find bugs? Yeah, maybe. Me personally, I don't. If I'm doing an assessment at work against a fake client that's .NET, I generally skip the fuzzing phase. Because you're really just kind of fuzzing the actual runtime itself rather than the application, and that's, you're not going to spend a bunch of hours on short-term engagement with .NET runtime. So, speaking primarily here about native code. So here's an example of a really high-value target or a high-impact bug that was found through fuzzing. I'm sure you remember the Beaudry buggers a couple of years ago. Joshua Drake was the researcher who was doing some fuzzing of the Android media server. This is a media server that's baked into the core of Android, also used in various other places. I think Mozilla had some of its code and things like that. So what he was doing was taking the core media server and fuzzing it with AFL, which we'll talk about in a minute. Basically just giving it an MP4 file, fuzzing the media server, and he happened upon crash. And this is the patch that was implemented as a result of that. And you can see what's missing here, overview, is just messing up some casting of integers, which led to an integer overflow, which led to a heap overflow, which he was able to turn into an exploit that, of course, could be triggered by an SMS or over a web page. Again, in the core of Android. So that's upwards of 1 billion devices that run some version of Android, and they all, for the most part, have this media server baked into it. So fuzzing is effective. You're going to find, you can potentially find really high impact bugs. Another really interesting case that I thought was cool is something Beaudry did on Project Zero. And he spent quite a bit of time fuzzing the Windows kernel. People started kind of paying attention to the fact that the Windows kernel is parsing font formats in the kernel itself, the ring 0, which from an attack surface standpoint is just a very interesting decision. I guess there's some performance benefits or something, but these are really complex file formats that are being unpacked in memory, in the kernel level. So that was a really interesting attack vector, and Beaudry here decided to take notice of that. So he spent about, I think it was 7 months, specifically targeting 2 font formats that are parsed in the kernel. Found 16 remotely exploitable kernel openings. So this is, bugs that you had a malicious font into a web page, and it's parsed in the kernel. You have remote command execution as so it finds a lot of bugs too. It finds important high-impact bugs, but it also finds a lot of bugs. Enough bugs that major corporations are starting to think about ways to monetize this or otherwise offer it as a service. If your organization has a really mature SDLC, you probably do fuzzing as part of that whole rollout. It's not that common, but people like Google, Microsoft, etc., they're fuzzing their products before they ship it. But they're also finding some use cases where they can actually offer that as a service to others. So Google just recently decided to do this OSS Fuzz project where they're taking important open source libraries and things like that and donating their infrastructure to run the code through their fuzzing infrastructure. So part of their whole make the internet safe and long-term. So they're having a lot of success. I actually just read something yesterday about a TLS implementation that they're running, and we were able to find some heap overflows and stuff like that just recently. The other thing that's really interesting, there's not a whole lot of public information, but Microsoft launched Project Springfield, which is basically, again, fuzzing as a service, but it's open for anybody to sign up. You pay whatever their subscription fee is, and you can use their infrastructure, use their management interface and everything to fuzz your own code. So, a great win for developers. Finally, I wanted to point out something that AFL found aside from the stage fright bug. if you go on their website, they actually have a Bug-O-Rama trophy case, and there's just like hundreds of bugs that are found in stuff like PHP, OpenSSL, like Firefox, Internet Explorer, Wireshark, Flash, like serious stuff. Because AFL is actually like kind of crazy, efficient, really cool. So I gave this talk actually yesterday to my AppSec group, and they told me, hey, you need more demonstrations because it was really cool. So I actually have. I wasn't going to do that, but then I found that I had an old Fuzzing run sitting around on Kali VM. So I was like, hey, why not? So the way AFL works, this is American Fuzzy Lock, awesome fuzzer. So generally what you do is make a folder that I have called I, and that contains all your input files. O is going to be your output for any crashes and fun. A long time ago, I was just kind of looking at this locate command. That's your typical locate command, like locate. So the way that actually works is the locate binary has a database of where everything is on the system, and then it parses that in order to look up what you're looking for. So I thought, hey, let's mess around with fuzzing on that. So here, what you typically do for with AFL works specifically on open source software and on POSIX, Unix kind of based environments. So I downloaded the source code here for mlocate. Let's see all this goodness here. So all you have to do in order to get this set up is just specify that you want to use AFL GCC as the compiler, and you configure it. And then what it does is the AFL version of GCC is actually instrumenting all throughout the code. And basically what I mean by instrumenting is it adds basically like probes all throughout the code that feed back into the fuzzer. It's really kind of interesting the way it works. So that way, when AFL is fuzzing it, it's constantly getting feedback like, hey, this input is triggering this code path, or this input is, coming this way and that way, and where is it exercising the code in the program? And it does this through this really, really cool instrumentation. And you can actually read a whole lot more about that on the website. You got really technical details, which is kind of a nerdy thing, but really cool. So anyway, now that you have it actually run, I can, let's see, just going to pull that back out here. So now all I need to do is specify, so in my I folder, I have a test database that I made up. I don't really anything interesting. So what I'm going to do is run AFL fuzz. I'm going to specify that the input folder is I, output folder is O, and then just run locate. Let's see, I think it's capital D. So when you run the locate command, you can use the D command, the D switch, to specify the database that it should use to parse. And I'm using this little @ notation because that's how AFL says, okay, this is where I need to stick the file that I'm going to use to fuzz. I'll just get it. I don't know how this is going to look on the screen. So it does a little test run. So I'm using a VGA adapter. Maybe I can. Okay. So right now it's complaining because I didn't do the right syntax. Let me just double check here. Okay, yeah, lowercase d. It does just some setting up information just to make sure everything looks good. So this is kind of what it looks like in AFL. I'm assuming maybe you haven't ever used it before. It gives you a whole bunch of really interesting statistics. Possible to dim the lights? The lights dim? Sorry, that's kind of hard to read. So there's a lot of really nerdy stuff here that's kind of awesome if you're into this sort of thing. but it gives you all these statistics on like how much of the code is actually being executed, where is it finding new paths, which files are triggering different things. What is really interesting to note here is right here in the stage progress, it says the exec speed right now is 296 a second. So this is effectively running the command with a different input, 200 and almost 300 times a second, which is not bad. I've seen it go a lot better. But yeah, so that's what AFL looks like. You can see I could just leave this running for a week and see what comes up. But that's all the effort that it takes to use one of the most powerful fuzzers that's available today. That's what I get for throwing in a demo with the rest. Okay, so back to key takeaways. That was, of course, fuzzing is effective. That demonstration of AFL was, I hope, is a nice transition into this point, and that is that anybody can do fuzzing. You saw everything I did from A to B, A to Z on that fuzz run for AFL. Really not that hard to just get up and running. If you want to do it, of course, you can write your own fuzzer. There's actually a lot of fuzzers already out there on the market. Some of these fuzzers are really ancient, like Spike or Axeman have been around for ages. They still, find bugs. They aren't, that effective, but they do some cool stuff. Mini Fuzz is listed there. That's actually that's kind of my go-to on Windows because it's like drop dead simple, and I've got a demo of that in a minute. It's super easy to use, and if I'm, as a consultant, just trying to get something done, in a set amount of time, then that's kind of my go-to. So there's that. There's Sully, which again is outdated, but has some really cool features. It fuzzes kind of over the network, and it can when it detects a crash, it'll save the PCAP of the traffic and give you that. It's got like a web interface built into it and all sorts of really cool stuff. So Sully's great if you have the patience to try and find all the old libraries and stuff that you need in order to get it set up. Some people have more patience than I do. So there's a lot out there. If you want to just kind of look at these and play around with them and get started, you can easily get started with something like that. Or you can always just write your own. If you think about it as a programming problem, this is conceptually not that difficult. So what you're doing is taking input, feeding it to an application, seeing what happens to the application, and then just looping that over and over. This is kind of like what computers are meant for. Repetitive tasks like that. So what I have here, this is hopefully not too difficult to see. On the bottom here, this is what's affectionately referred to as Charlie Miller's 5 lines of Python buzzer. So Charlie Miller, you may have heard of him. He had a talk back in 2010 where he illustrated this code here. And basically, if you read it here, it's just taking some random number, and then it's going to use that as the number of times it's going to do some sort of mutation inside the input buffer. And then what it does is take that input buffer, take a random location in that input buffer, and just flip that byte to some other byte. So just kind of randomly picking something and swapping it with something else, giving it to the application, and then see what happens. So I wrote the rest of this Python around it just as like a, I don't want that out of context. The only thing that's missing here is actually like launching the application and monitoring it, which to do the most basic way would only take maybe another 10 lines of code or something like that. So the point is, it's really not that difficult if you've got any kind of programming experience or interest to roll your own. So if you're going to roll your own, or even if you're just out there looking at what's available, all the fuzzers in general kind of fall into these two categories. You could probably make a case for more than two categories. I think for the purposes of an introductory talk, they kind of fall under these umbrellas. So mutational is kind of what we've been discussing for the most part. It's more common, and that's just you give your fuzzer a bunch of examples of known valid input data. Then the fuzzer's job is to take that known good,
flip it around, screw with it a little bit, start trashing it maybe, feed it to the application and see what happens. That's kind of easy enough to understand. The generational is it's an interesting approach that takes a lot more work ahead of time, but is very effective in its results. And that is just to basically teach the fuzzer the semantics of the data format that you're trying to represent, and then have your fuzzer build dynamically those valid test cases. So, for instance, if you're fuzzing a browser and you want to teach your fuzzer how to make an HTML page, then you're going to say, here's a big list of tags, your anchor tag, your HTML tag, body tag, division tag, whatever. And then here's the different attributes that could go in there. Maybe even if you wanted to really get crazy, here's a script tag and there's some JavaScript, stuff like that. So it's a lot of work to teach your fuzzer all of that in the beginning, but you're going to come up with some really interesting results that you might not see out in the wild. With a mutational fuzzer, the amount of work that goes into the beginning is finding good test cases, because if you only find, say, 3 different input files and they're basically the same, you're not going to have that much of a different result for the 3 of them. If you can find 100 different files and they're all really small and diverse, then mutations can find some really interesting test cases that way too. So if you're anything like this curious caterpillar, you might be wondering which one should you use. It's really just application dependent, also dependent on kind of your skill set. If you want to take the time to build out a dictionary for different file formats, it's going to pay off in the long run for your generational fuzzers. If you just really want to get up and running just really fast, mutational is kind of pretty good. So AFL, the demonstration I did, it actually is, it's complicated, but it's a mutational fuzzer. It does have a dictionary mode where it does more of this generational kind of thing, and you have a certain syntax that you build out a file with, and then it takes those keywords and kind of clobbers them together and sees what it comes with. So yeah, choice is yours. Both good. Before you fuzz, there's these really important fuzzer helpers. I call them helpers. I don't know if there's a better term for that. So address sanitizer or async, you've seen that around. Beaudry, those are both on the Linux side. They are specifically made to point out memory errors. So Beaudry itself is an instrumentation framework that you can use to build these analysis tools. AFL kind of has some of that built in, but you can use that as well, just another option. Address sanitizer. There's also some other sanitizers that are out there. If you Google address sanitizer, there's some other stuff that are meant for finding more specific bug classes. Address sanitizer is great for use after freeze and buffer overflows and that sort of thing. On Windows, page heap is the way to go. This is a tool that you can use that's built into the debugging tools for Windows. And what it does is tells the operating system, okay, whenever you launch this application, when that application requests memory, put some guards around that memory. And if there's ever any incursion into that guard page, it'll set off an alert. So what this is great for is there's so many times where if you're fuzzing something, you may get some memory corruption on a heap, for example, but you don't notice it right away. So if you have a heap overflow, you overwrite 3 more objects on the heap, but you don't use those objects until much later on in the program, and then it crashes, then you're triaging your crash and saying, okay, so what happened here? You look at it and you're like, somehow these objects are all screwed up. I don't know what happened. That's because the corruption happened, way earlier in the program's life cycle, but you're not noticing it until later. So, as the wise David Kaminsky puts it, you want to be using these tools. You're going to be missing a lot of crashes. I don't know if I'd say almost all of your crashes, but it's a good idea. Oh, he mentions G flags here. So page heap was a standalone application, and then just more recently, Microsoft bundled into their G-Flags utility, so G-Flags has a page equal. So when you're fuzzing, this is kind of what it looks like, especially useful if you're going to be building your own fuzzer. You're going to spend your time, whether it's mutational or generational, actually creating the input, finding the valid input files, or building out your generational syntax. But when you actually run the fuzzer, then that's when the fuzzer does something with that input. It's either going to take that input and mutate it, or it's going to generate the input that it needs. Either way. So then it launches the target. It actually debugs the target. So here's something I didn't really realize until I built my own, is that in a sense, fuzzers are really just purpose-built debuggers. Like, they attach into a program and they're monitoring it for, usually crashes, other things too. So it's basically just a debugger that only cares about crashes and is just constantly running the thing in a cycle. So it launches the target, debugs it, gives it the actual input, whether that's just reading from a command line or reading from standard in, whatever. And then while it's parsing that input, that's when your debugger is monitoring and hopefully looking for crashes. Well, looking for crashes, hopefully getting crashes. At that point, it triages the crash. You're going to want to save off the input file that caused the crash and maybe grab some data, like here's the address at which it failed, here's some of the memory that was around there, here's what the registers look like, and that sort of thing. It's kind of important to define what is the input that you're looking at. So in some cases, it seems obvious on just the face of it, but it's kind of a whole mess of looking at the attack surface of the application. So you might think of something like Adobe Reader. What's the attack surface? Well, it's a PDF. That's kind of a simplistic way to put it. So it's an interesting case because, number one, PDFs are a very, very complex file format that can have embedded, files of any other type embedded into it, even run JavaScript. PDFs can run JavaScript. But even thinking outside of that, like Adobe Reader calls out to the network to get updates, right, to see if it's the latest thing. So there's a network attack surface there too. Adobe Reader is going to be reading registry keys, reading configuration files, environment variables. All these things are something that your application may or may not be touching. Depending on the application, you can have even COM endpoints, RPC endpoints, COM interfaces. So that's preparing the input. When you're actually doing the debugging, these are the functions that you would use in writing your own debugger. So in Windows, you would use the create process API, and you would actually pass it a debug flag, and that tells the operating system, okay, I'm going to be listening for debug events while this application runs, so let me know how it goes. And then you just use this wait for debug event kind of in a loop, just to see if there's ever anything happening that's of interest. Same kind of thing on the Linux side, ptrace. It's kind of identical. It's not identical, but it does the same thing. Just polls for, let me know when something interesting is happening. So after that, hopefully you're monitoring your target, hopefully getting a crash. So now you have to triage the crash. These are two utilities. There's not, there's not nearly as many of these triaging utilities as there are fuzzers, but these are two that I think really stand out. So Bug ID by Skyline is really, really cool. It's like one of my favorite things right now. What that does is after you find a crashing test case, you can give Bug ID the test case and the application that you used, that you were fuzzing your target. And what it will do is run the application under a debugger, give it that input file, and just gather all sorts of data about what's going on at the time of the crash. So it gets snapshots of memory, a whole disassembly for you. It categorizes, is this exploitable, is this a security issue, how could it be exploited, and it generates a really nice HTML file for you too. Just for the added win. Crashwalk is similar. That's a little bit older, but same idea. It's more for, it just outputs to the command line, but it gives you some really useful information as well for any crashes that you get. All right, so I personally fuzz more on Windows. I like Windows a lot. So I'm going to show you mini fuzz. So this is the mini fuzz interface, which kind of looks terrible on this projector. Ooh, that's rough. Okay, we'll power through this. So as you can see, hopefully, maybe, on the top here, when you launch MiniFuzz, this creates a MiniFuzz folder here. And it has a folder here for crashes, for a run log, and just a temporary kind of scratch space. Templates is kind of similar to the I folder that we used in AFL. This is what holds your input samples that you're going to use. So it creates that in the same directory that you're running in. I thought just for a good visual demonstration, we could just run this against MS Paint. You kind of know what the input is for MS Paint, like it's going to be taking a picture file. It's kind of so you can specify your target to fuzz there, any command line options you want to pass to it. I'm actually going to bump up the allow process to run for just 1.5 seconds. So the big difference between Windows utilities and Linux utilities, a lot of these Linux utilities, you tell it to do something on the command line, it does it, and then it quits. Which is great because if you're running something in a loop, you don't have to wait for it to quit, it just kind of quits automatically. The case with Paint, though, is a little bit different because it's designed to use your input. So it's not going to shut down. What MiniFuzz does, and most debuggers that run, or most fuzzers that run on Windows, is after a certain amount of time, they'll just kill the process. So this has a couple of different options in that dropdown. And it's hard to read. A couple of different options for how it kills the process. This is just injecting a thread, but it doesn't really matter. So anyway, what I'm going to do, I got this all set up here to run Paint against a picture of a nice little baby on a laptop. So you can see a lot of the time, the changes that it makes to the file doesn't really affect it. Like that looks perfectly normal. Sometimes it's a little bit glitchy on the bottom. Sometimes the whole thing is all glitchy, which is a kind of cool way to see, like visually see what the mutation is doing to the file. The main thing you'll notice here, you remember AFL is getting about 300 executions a second. We're getting an execution every 1.5 seconds. So dramatically less effective. But AFL is kind of unique. It's pretty awesome. And this is just something that many fuzzers can't touch. So I'm going to stop the fuzzing there. That's kind of what it looks like. And I could tweak the runtime to maybe only let it run for maybe even up to half a second because it doesn't take that long on this VM to parse an image. So we can tweak that a little bit. There are, as you'll notice down here, this is where it keeps track of crashes. And it is finding crashes in MS Paint. I don't have any MS Paint O'Day, so don't ask me. This is actually just a false positive. It's all at the same address. And something about screwing with JPEGs causes it to report this as a crash at that specific address. I really don't care enough to figure out why, but just be aware that sometimes in your fuzzing you can find false positives. So that's a really simple example. Of fuzzing on Windows. Sorry about that. Okay, so we talked about how fuzzing is effective. You're going to find bugs. Fuzzing is not all that hard. It's your friend. It's easy to do. Thirdly, it's easy to learn, but it is hard to master. So if you looked at that demonstration on Windows, it was pretty lame. Like, I'm not going to lie. We looked at how cool AFL was. We looked at Windows, and I was like, hey, why even bother? So, naturally, the question arises, can we do any better on Windows? So I was thinking about this. What are some ways we can kind of up our fuzzing game here and get some better results? So it dawned on me, the cool thing about a lot of these utilities on Linux is that they just kill themselves automatically. They're not waiting for user input. So what if we just patch paint so that as soon as it's done parsing that file, it just exits? Seems like a good idea. Naturally, the question would then arise, where do you have to do that? So this is where it gets into maybe a little bit more advanced, because you actually have to do some reversing and debugging of MS Paint. You actually have to know your target, to see what you have to do and where you have to do it. So, but just looking at it logically before we even dig into the code, you got to figure there's a point in MS Paint that's going to start up, get everything loaded that it needs in order to parse the input. Then it's going to look at the input that you specified. It's going to parse it, actually draw the picture, and then normally it's just going to wait further instructions at that point. If you want to start drawing a smiley face on the baby or whatever. What we want it to do is the first two steps, that's fine, but as soon as it's done parsing the input, at that point, just die, go away. That's all we care about is the parsing. If there's going to be an interesting crash, it's going to be while it's parsing it. But figuring out where that actually is a little bit of a beast. So I had to put on my WinDebug wizard hat and came up with this giant monstrosity. So what this does is anytime an application, there's several APIs that Windows offers for actually opening a file, but they all kind of funnel down to nt-create file, which is in ntdll, and that's basically just a wrapper around a system call that calls into the kernel to do the file opening. So that's an ideal place to set a breakpoint. So what I'm doing here is just setting a breakpoint on nt-create file, dereferencing a couple of pointers on the stack, or actually in registers because it's 64-bit, to see what file name is being passed to this nt-create open file, or nt-create file. What it does, so it looks at that, it compares that file name to star or baby.jpg to see if that's what we're looking for. If it's not what we look for, then just don't break, just continue. Otherwise, break there. So the idea is we're going to look at what function is opening the file, look at that function, and ideally that's the same file that passes that input on to parsing function, and then as soon as it returns from that parsing function, that's where we want to kill it. So I ran this in WinDebug, got this, which probably, that kind of shows up all right. Got this big stack trace, so it actually did break. You see that very first line, it prints out like, hey, okay, it's trying to open baby.jpg, so this is what we're looking for. So I did a stack trace, and all these red lines are pointing to functions on the stack that relate to opening files. So I'm looking further down, and this is the parent function that calls all of these functions that are related to opening files. So, this is promising. This is kind of what I'm looking for. I did some reversing. Turns out it looked like it was a good place to go. I wasn't positive, but I had enough information to kind of say, yeah, let's try this. Opened it up in IDA, and decided to just hex edit it. So there's a lot of ways to do patching, dynamic patching of binaries. This is just a hex editor. Found the exact code that was returning from that function. So at the end of that function, normally it would just return back and carry on. But instead of returning, I wanted to kind of kill itself there. Search for the hex of the instructions that I was looking for. Inserted my own hex version of the assembly at the same spot, and this is the result there. So I took the patched version, ran it through a binary differ in IDA called diaphora. And you can see before what it was doing is fixing up the stack and returning back to the parent function. What I'm doing instead is clearing out the RCX register and calling exit, so it's basically just exiting with a 0 status. So everything looked good, and I figured I would try it out. Let's try it out. You gotta figure if I'm doing a demo, you probably know what to expect. So this is MS Paint patched. I'm going to leave everything else the same, except for actually I'm just going to knock the allow process to run for 0.5 seconds. And I'll show you why in a second. So anyway, now when I start fuzzing, sometimes it's going to come up with those error messages. But yeah, you can kind of see, sometimes you can actually see like a faint shadow of the baby before it actually dies. But it's a significant win. So it's still going through the parsing logic. You can see sometimes you do actually see a baby there, so you know that the program is going far enough to actually parse the input that you're telling it. Now, I did drop it down to still kill it after half a second, because sometimes, you're trashing the input file, so you could be overwriting some kind of vital structure, maybe the signature at the front of the file, something that MS Paint actually needs to say, oh, hey, this is a JPEG, I can handle this. Sometimes it gets overwritten and MS Paint says, I don't know what to do with this. Screw you, here's your pop-up box. So I just have it kill it after half a second. But anyway, you can see it took a little bit of work, a little bit of reversing, but the payoff is pretty significant there. So I'm really good at PowerPoint. Can we do even better? Well, yeah. Hopefully you were thinking that yourself. So yes, we can do even more better. So there's a really cool technique called in-memory fuzzing. And I'm focusing primarily here on Windows again because I like Windows better. So in-memory fuzzing, basically what it does is uses this tool here to create a snapshot of the process memory. Really kind of a neat function that Windows offers. Like, I didn't really know about this before doing some of this research. But you can use it, as you can see there, to take a snapshot of the process, including its heaps, modules, threads, all in use in the process. So it's just like as if you pause the application, you make a snapshot, set that aside, and then you can use that to revert. So the way you can use this in fuzzing, going back to what our flow looks like here, is you start the application, before you parse the input, you take a snapshot right there. So this is kind of the recovery point. Take a snapshot and then let it proceed through the parsing the input or whatever. And then instead of actually exiting like we had in our patched version, it's just going to revert back to that snapshot. So if you think about the first example, our main sources of slowing things down, or roadblocks, if you will, was that it had to kill the process after a certain amount of time, and then it had to start up a new one, which isn't that big of a deal, but you saw how slow it was. So in our second one, we significantly improved that, but it still has the bottleneck of starting a new process, which is when you're talking about CPU level instructions and things like that. It's a really expensive, costly process to call into the kernel, switch CPU context, and all this sort of thing, just so that you can get another execution cycle. So what we're doing here is just cutting that out. So it takes a snapshot, parses the input. As soon as it's done parsing the input, revert back to to the state that the process was in before it parsed it, and then it's going to, of course, prepare the next test case, and then just let it execute again. So really neat concept. I didn't have time to put together a demo, so I'm sorry for that. But just know that that's something that's out there, something that you can do. I'll leave it as an exercise for the reader. So other more advanced things that you can look into, I'm not going to get into this now, but just some really cool techniques on the left side that are really helpful for again, upping your fuzzing game. Stuff that is really effective. Here's some tools on the right side, different versions of some of that stuff, but things that you can use to really dig into a binary, see what it's doing, and monitor it during your fuzz runs to hopefully get something a little bit more useful. That being said, hopefully you all have some questions for me.
I do.
If you think of questions, I'll be around. Also, this is me, so you can find me online. Oh yeah, so I'm also with OWASP, the co-leader of OWASP. Tampa, so if you're here local,
check us out. We're doing some really cool like lunch and learn and stuff like that. I do a free lunch on like a Friday afternoon. It's pretty cool. Yeah. So it's a local. You just Google OWASP Tampa. You'll see our page. It's part of the main OWASP page. Yeah, you can come check it out.